In this video, we discuss the suitability of different algorithms for a specific task and dataset in terms of execution time and space. So this video provides an introduction on how to compare the suitability of the various algorithms covered under the AS specification. It assumes you're already familiar with the 4 algorithms you need to know about at AS level. So if you've not seen them, we suggest you go back and watch the 4 videos listed here. So beyond understanding the basics of each algorithm, it is important to consider how suitable an algorithm is for a specific set of data. The ultimate goal should always be to design algorithms that will run as quickly as possible and take up the least amount of memory as possible. To figure out whether one algorithm is more efficient than another, we need to consider its complexity as a function relative to the size of the problem. But what do we mean by this? Well, consider the 2 pseudocode algorithms shown here. Both are taking a single integer parameter n and totaling up a set of numbers before returning a result. So if n equals 10, both algorithms performing the sum 1 plus 2 plus 3 plus 4 all the way through to 10, and it returns 55. Both algorithms perform the same function, but in very different ways. The first is using a for loop. The second is using a single one-line formula. So which is better? It depends how well they perform as the initial input value n scales up. So let's start by considering the for loop. There is one operation carried out outside the for loop when the value of 0 is assigned to sum. So this will execute once. There's one operation carried out inside the for loop, and this will execute each time the for loop iterates. We can see that no matter how large the input value n becomes, the highlighted operation only ever executes once. In terms of the algorithm's complexity as it scales, this line of code is the significant one. As soon as n becomes anything other than a trivially small number, the amount of complexity that single operation is adding becomes insignificant, so essentially we can ignore it. Therefore, we can see that the algorithm's performance declines in a constant and direct relationship with the growth of the dataset. The second version of the algorithm contains a single line that performs the calculation. We can see that the line only ever executes once, regardless of the size of n. The result of this algorithm may be the same as the first one, but it will always execute in the same time, regardless of the size of the dataset. Algorithms can be measured on their efficiency, which has 2 measures: time complexity, how much time they need to solve a problem, and space complexity, the amount of resources, e.g. memory, they require. Some algorithms are more efficient time-wise than others, whereas some are more efficient space-wise. Remember, the goal should always be to design algorithms that will run as quickly as possible and take up the least amount of memory as possible. Now, we looked at time complexity of these 2 algorithms earlier and concluded that time-wise, the second version without the for loop would execute quicker. Here we've added an additional line of code that appends the result held in the sum variable to a list. Again, the mylist.append sum line of code has to execute n times in the first version of the algorithm, as opposed to executing just once in the second version. Assuming again that the input value of n is 10, the first algorithm is going to require 10 times the amount of memory to fully execute. In this example, the first algorithm is worse in terms of both its time complexity and its space complexity. Later in our full A Level videos, we will look at time complexity and space complexity in more detail. So let's take a look at the 2 searches you've learned about in more detail, the linear search and the binary search. In this section, we will compare the 2 searches and see which performs better when trying to locate an item from a large data set. So let's imagine a data set that contains every single possible combination of 6 letters from A through to ZZZ. So that's over 300 million possible combinations. We're going to look for a string of 6 Bs. Let's assume this list is unsorted, so we can use a linear search without any issues. Not that it would matter, we could use it on a sorted version too, but that's our starting assumption. We find our target item after 75,000 linear searches. Not bad. Considering an unordered data set, it could just as easily have been located in the very last position. So we got lucky. Let's try to find the target item of 6 Bs using a binary search to see how it compares. Now remember, the first thing to do is sort the data, as a binary search can't run on an unsorted data set. Then we set the lower bound as the first item, and we set the upper bound as the last item. And we set the midpoint as the lower bound plus the upper bound, and do an integer division of 2. After the first search, the midpoint is now at NAAAAA, which is greater than BBBBBB. So we know it must be between the lower bound and the midpoint. The upper bound now becomes the midpoint minus 1, which is 154 million. After the second search, we find the midpoint is GN and then 4 A's, which again is greater than what we're after, so we still must be between the lower bound and the midpoint. The upper bound now becomes the midpoint minus 1, which is 77 million, and we set another new midpoint. So you can see the power of this algorithm, especially when used on large data sets. After only 3 iterations of the binary search, the size of the data set we're searching against has been reduced from over 300 million to just 38 million. Let's fast forward a little now and watch the algorithm play out. Divide and conquer allows us to discard half the entire data set with each successive iteration. We're only 13 searches in, and the data set has been reduced to just 37,707 items. Using a linear search, we would still have only checked the first 13 items by this point, and we still have well over 300 million more to check. If we skip to near the end of the algorithm, we see that it took just 27 iterations to locate the item. By comparison, if we'd used a linear search, it would have taken over 12 million iterations. The binary search algorithm has clearly outperformed the linear search algorithm in this situation. But in the exam, be careful of using simple statements like the binary search algorithm is better. The binary search is a more complex algorithm than the linear search, so for small data sets, the linear search can actually outperform it. However, the binary search quickly outperforms the linear search as the data set increases in size. Now this graph here is assuming the data set has already been sorted. Now, as a linear search doesn't require a data set to be sorted first, this has no impact on how quickly an item can be found. If the data set you wanted to search against is unsorted, you should consider the additional time it would take to sort the data set before you could even execute a binary search. The time it would take to sort a large data set could be significant and will all depend on the efficiency of the sorting algorithm you decide to use. So here's a nice little summary table of the linear search and the binary search. You might like to pause the video here and take some notes. Having watched this video, you should be able to answer the following key questions. How can your choice of algorithm be affected by the current state of a dataset? And how do different algorithms impact speed and memory use? So that's everything you need to know for the AS level specification. If you're interested in what's covered in the full A level, we're going to touch briefly on it now, although of course if you are an A level student, we have dedicated videos on these. So when comparing algorithms, we also need to consider the situation. In a best case scenario, a linear search will always find the item on the first attempt, e.g. if the item in the first location of the dataset is the one we're after. A best case scenario for a binary search would also find the item on its first attempt, e.g. if the item we're after is at the midpoint of the dataset. So if we just consider the best case scenario, you could argue that the algorithms are both as efficient as each other, regardless of the size of the dataset, and that statement would be true. Of course, the comparison changes when we compare them based on an average or a worst case scenario. A binary search quickly outperforms a linear search as the size of the dataset increases in all situations other than a best case scenario. Now at this stage you don't need to worry too much about terms such as constant, linear or logarithmic time complexity. What we've covered here is perfectly sufficient for the AS level course. Later in our full A level videos we'll cover algorithm complexity in more detail. If you are studying the full A level, you will cover this in more depth, and we have a separate set of videos on something called Big O notation. Now, Big O notation is used to describe the complexity of an algorithm in terms of how well it scales. As a dataset grows, so too can the number of cycles of processing time and memory space requirements, and this is known as scalability. Big O notation describes this effect, taking into consideration best, average and worst case scenarios. We know that getting to grips with data structures and all the algorithms associated with them is a very tricky area of the course, and so we've produced a book called Essential Algorithms for A-Level Computer Science that's available on Amazon. It covers all the data structures you need to know about, along with the algorithms you need to perform on them, and it covers all the exam boards. We overview each data structure, discussing its typical applications and the operations you can perform on it. We provide a QR code that jumps off to a useful page of additional resources. We then take each data structure and the algorithms you need to perform and present them first in simple structured English, then in a diagrammatic format, then in pseudocode, and finally we present you with fully coded algorithms which you need to cover on the data structures in both Python and VB, so you can actually code them up and practice them yourselves.